Okay, hello everyone and welcome to Probability and Statistics. We're going to do a covariance and correlation problem for a continuous random variable set. Our function that we're given is c, which is actually fairly easy to start with, but we have to figure out what c is. But before we even do that, I want to introduce the equations that we'll be using. Covariance, often shown as sigma xy, is equal to the expected values or the means of xy, and then the individual means of x and y. And then the correlation is the variances and over the covariance, underneath the covariance. So, or the standard deviation, however you want to look at that. Okay, so solving for c, first thing I want to do is kind of draw a picture of where my limits are based on this. So, I go ahead and sketch this out. I've got x from 0 to 5. I'm going to put 5 out here. And then I've got y from x minus 1. So I'm going to say minus 1 is right there, going up at 45 degrees. Bigger point there. And then x plus 1. So 1 right there, going up like that. And if you draw 5, that right there. Okay, so, and then x is greater than 0. It's going from 0 to 5. And then we got y from 5 there. Okay, cool. That's pretty good. Let me make sure I got all my notes right here before I start showing something that's wrong. Okay. There's also one more condition. Y is greater than 0. Forgot to put this up here because it was off by itself. Y is greater than 0. So now we have y greater than 0 right here. So the area that we're looking at is this. So this is, we're trying to find the probability of these points in here. This is our complete function, our complete PDF, or distribution, probability density function basically. So now that we know this, we can go ahead and set up an integral to figure out what the area of this is, to figure out what c is. But you'll notice that you can't just do a simple double integral because you have this kind of change in shape going on down here. You can't go, oh, from the y's and then the x's along that in that way because it's just not there because of this line right here. So we're going to split it up into two double integrals right along there. And we'll go from y from 0 to x plus 1, and then from x minus 1 to x plus 1, and then x will go from 0 to 1 and then from 0 to 5. And setting that up, we're going to have the integral from 0 to 1 for x, and then the integral from 0 to x plus 1, c dy dx. C is our function. Okay, plus the integral from 1 to 5, and the integral from x minus 1 to x plus 1, c of dy dx. And then you set that equal to 1, because that's how you find the joint probability density function, which you have to do in order to get c. Now, I'm not going to show all the calculations for these because constant is a fairly easy thing to integrate. So I'm just going to go ahead and solve this out. You're going to end up with c of 1/2 plus 1 over here plus 2c of 4 over there, and when you solve that all out equal to 1, you should end up with c equal to 2 over 19. So that's our joint PDF. Okay, so now we can start solving for the covariance and correlation now that we actually have c. So, going ahead and doing that, I'm going to cover up a chunk of this so we can again see the top here, see the equations we're working with, at least for a little while. Okay, so c is equal to 2 over 19. Okay, so in order to get sigma x, we need to find sigma xy. So we need to get the expected value xy, expected value of x, and the expected value or the mean of y. So mu of x equal to e of x is equal to 2 over 19, which is our constant, times the integral from 0 to 1, the integral from x plus 1, times x dy dx, because e of x is equal to basically the integrals over the points are x, all the points that are relevant, of x times your probability density function, fxy of xy. which in this case is just 2 over 19, so we take it out and we leave the x in there to multiply through. So that's how you set up the mean. Now again, this is going to have to be a double integral plus 2 over 19 because again we have that odd-shaped graph that we drew earlier. So 1 to 5, and then the integral from x minus 1 to x plus 1. And since it's not conditional, you use all the points, you use the entire range, x, dy, dx. Okay, so again, this integral is a little bit tougher because you actually have a constant here, but it expands fairly easily, and I don't want to have to show the calculus because this is statistics. So when you finish this all up, you should, after a little while, taking both of the integrals, they should both reduce to equaling 2.62 is equal to e of x. Okay, so that's your first e of x. Now e of y, or mu y, equal to e of y. Again, using the same equation, but instead of rx will be ry, is equal to, I'm going to change up the notation a little bit too, just factor out the 2 over 19 because it's a constant for both of them. The integral from 0 to 1, the integral from 0 to x plus 1, y dy dx. And you can see nothing really changes except changing this y to this x to y between these two. So there's no complicated trick you really need to remember, or way to set up the integrals in any kind of way for this. Plus the integral from 1 to 5, the integral from x minus 1 to x plus 1, y dy dx. Okay. Normally, hopefully your professor doesn't give you double integrals too often, but if he ever does, this is a good complicated problem. It's easier to go backwards from this than to go forwards up to this kind of thing if you were only introduced to a single set of double integrals. As you calculate this out, you should end up with something along the lines of, let me grab something. Alrighty. Something along the lines of 2.65 equal to e of y, or e of capital Y. I don't really recognize the capital or the lowercase too much just because it's kind of confusing, but if for some reason you've been taught that, fine. Okay, and then e of xy. This one is not any more difficult than the other ones. The only thing that changes is that since you have this function with respect to x and y, instead of just going all the points from x of f of x, you go f of x, xy. So that's all there is to it, really. You can just consider these basically as a single variable for doing the mean. So we've got the integral from 0 to 1, integral from 0 to x plus 1 of xy dy dx, plus the integral from 1 to 5, integral from x minus 1, x plus 1, xy dy dx. And then doing some more calc, getting that all solved out, you should end up with this equaling 8.78, or something fairly close, equal to e of xy. Okay, so now we have that, we can solve for the covariance. So sigma xy is going to equal 8.78, using this equation right here, 8.78 minus 2.62 times 2.65. And when this is all said and done, you should end up with this equaling 1.75, or somewhere close to that. It may not be exact, but this can vary within like plus or minus 0.4, depending on how many digits you took, how much you cut, and so on and so forth. Plus or minus 0.4. Okay. Alrighty, so there you go. There's the covariance. Not too darn difficult to do, just these double integrals up here for all these things. And all you have to remember is take the function that you were given, the joint probability function, and then multiply it by x for whatever, multiply it by the variable that you're using to find the particular mean. Alrighty, so now for the correlation, rho is equal to sigma xy all of the square root of sigma x squared times the square root of sigma y squared. Okay, so we have these two variances underneath here, the square root of these variances, which is going to give you a standard deviation. So we have to solve for these. We have sigma xy up here. So going ahead and doing this, the variance of x is equal to sigma x squared is equal to the integral the equation that you use, x minus mu x squared fxy of x and y dx dy. Sorry, this is kind of scrunched up, but dx and dy. So going ahead and doing this, again, it's a double integral. You have to do this for both dx and dy. For vy, you just go ahead and change this variable to y. So it would be the integral vy is equal to the integral of y minus mu y. And mu y is from up here, remember. You're using the means, mu y. So the ex and ey is kind of a confusing system because these two flip back and forth and these two flip back and forth depending on where you are. So it's something you really have to learn, but hopefully it's not too darn difficult to memorize those of xy dy dx or dx dy or dy dx, however you want to set those integrals up. The double integral, it doesn't really matter. Okay, so just to kind of show up the setup for the vx, I'm not going to do vy because it should be fairly obvious and it's set up exactly the same. It's going to be the integral from 0 to 1, 2 over 19. I'm taking the value of e of x 2 over 19 to the outside, so we don't have to think about it. The integral from 0 to x plus 1 of x minus 2.62 mu of x squared plus the integral from 1 to 5 and the integral from x minus 1 to x plus 1 of x minus 2.62 dy dx. dy dx. If you solve that out, you should end up with mu or sigma x squared equal to 1.93. Okay? Then you can go ahead and then if you do sigma y, where you're just replacing this with y and this one with 2.65 dy right here, then you should end up with sigma y squared equal to 0.21 about-ish, however many decimal places you take. So then the correlation is going to equal 1.75 all over the square root of 1.93 times the square root of 2.1, and this should equal 0.98 rough. So your covariance is your correlation right there. Okay, now this problem is really not that difficult. These equations are fairly easy to use up here. The tough part is just getting the values to have to put into the equations. I mean, we had to go through the whole solving for C right here to get our joint PDF, and then we had to find the means, and then we had to find the variances, and then put them into these equations. They both required 2 sets of double integrals. So it gets kind of hairy in the calculus, and that's where you can make the mistakes, missing a negative sign or something. But hopefully you don't have anything too darn complicated, and it stays in kind of the single variable or single constant that you have to solve the integral for, so it stays a little bit easier. But overall, the concept is not that hard. You do the range for x, and then you solve for e of x, and you just have to remember these, or the range of y, and you solve for e of y, and that's pretty much all there is to it. The toughest part is the calculus.